Question 26. A project requires activities A to F to be completed. The activity chart shows the immediate prerequisites and duration for each activity. So part A, by drawing a network diagram, determine the minimum time for the project to be completed. And part B, determine the float time of the non-critical activity. So let's have a look at the table. So we have activity A, does not have any prerequisites. So we can draw a vertex here, and that's our start. Our start vertex, and we'll draw one edge representing activity A, and its duration is 2 hours. Now, activities B and C both depend on activity A being completed. So those two can branch off, one there and one there. So activity B takes 6 hours, and activity C takes 5 hours. Now, as we do those, I'd like to sometimes tick these off to say, yep, I've now got them accounted for in the diagram. Okay, activity D depends on activity B. Okay, so now what I'm going to do though is, rather than drawing it across, notice that activity E depends on C and D, but D depends on B. So what I could do is draw activity D as an edge joining B and C with a down arrow like that. So there's activity D, and D takes 2 hours. Now, activity E depends on C and D. So C and D meet up at this vertex here, which means I could draw an edge this way, and this is activity E, and that takes 4 hours. And finally, activity F depends on activity E, and that takes us to the end. And there's our end vertex. Okay, your diagram might look a little bit different. That's fine, as long as the connections and the sequence of activities match the table, then that's not an issue at all. Okay, all right. So we didn't have to use any dummy activities or anything. Let's now do the critical path analysis. So I might draw some dominoes here. And there's one here as well. One here. One here. And one here. Okay. So from the start, A must be on the critical path. It's the only activity from the start. So there's 2 hours there. Now, from activity A, we have activity B. That takes 6 hours. Add it onto 2. And this will be 8. So this is we're doing the forward scanning now. So this is to find the earliest start times of all the activities. Now, what do we put in this box here? 2 plus 5 is 7. 8 plus 2 is 10. We put the higher number. Okay, there's 2 ways to get to this vertex. And whichever way takes the longest, that's what you need to write down. Because we can't start activity E unless all these activities are completed first. Now, the rest of these activities are all on the critical path because it's the only path. So 10 plus 4 is 14. 14 plus 1 is 15. So the minimum time is 15 hours. Now let's do the backward scanning. So starting from 15, 15 minus 1 is 14. 14 minus 4 is 10. and that makes sense. Now, we've got 10 minus 2 is 8. Now, there's two ways now to get to this vertex here. We can do 10 minus 5, which gives you 5, or we can do 8 minus 6, which gives you 2. You put the higher number now. So 10 minus 5 is 5. Now, let's determine the float time of the non-critical activity, because this is what we've just done there, is to determine part B. So the non-critical activity, okay, is the activity that comes after this domino here. So the float time of the non-critical activity is activity C. So the EST, earliest start time for C, is 2. The latest start time for C is 5. Therefore, the float for C is equal to 5 minus 2, which equals 3 hours. Question 30. The network diagram shows the tracks connecting 8 picnic sites in a nature park. The vertices A to H represent the picnic sites. The weights on the edges represent the distances along the tracks between the picnic sites in kilometres. Part A. Each picnic site needs to provide drinking water. The main water source is at site A. By drawing a minimum spanning tree in the space below, calculate the minimum length of water pipes required to supply water to all the sites if the water pipes can only be laid along the tracks. So what we're going to do is just draw in the vertices first. Okay, so there's A. Okay, we got B. Okay, we've got C up the top. Okay, G up the bottom. Okay, we've got F here. Okay, we've got E here. And we've got D up the top. Okay, there we go. And we've got H somewhere here, just above F. Okay, so what we're going to do is we're going to apply Kruskall's algorithm. Kruskall's algorithm is probably a little bit easier than Prim's. It's just a matter of just selecting the lowest weight edges first and in ascending order. So we can select edge GF. Okay, so it connects those two. Okay, now let's have a look. There's no more edges of weight 1. Let's have a look at the edges of weight 2. We've got 1 there between G and H. Okay. Yep. Okay, so that no other edges of weight 2. Weight 3, we have 1 edge here. Okay, which is CH. Okay, so that's that one done. Okay, now weight 4s. Okay, we've got AB. And we've also got CG. Okay, just here, CG. But we can't use that edge because that then creates a cycle. Okay, a closed path. So we can't use this edge here. So that's all the weight 4s. What about the edges of weight 5? Okay, so we've got BC. Okay. Okay. And we've also got DH and EH as well. Okay. So what I'll do is I'm just going to draw in the weights as well. That's a 2, that's a 1, that's a 5, that's a 3, and that's a 4. Now, to get the minimum length, we just add the numbers. Okay. So we have 1 plus 2 plus 3 plus 4, and we've got 5 plus 5 plus 5, which is 15. And so the answer is 25. Now part B. One day, the track between C and H is closed. State the vertices that identify the shortest path from C to E that avoids the closed track. Okay, so CH is now closed. Okay, so that's gone. Okay, but we need to get from C to E. So we can either go CG, CGHE, we can go CGFE, so there's a weight 7 there. We could go CDE, so that's 7 plus 5 is 12. So we try and identify this, whichever part's the lowest weight. So we have a 12, CDE is 12, so I might just write these down. Okay, so there's 12. We have CGFE. Okay, CGFE, so 4 plus 1 plus 7 is also 12. Could we get one that's less than 12? CGHE. So 4 plus 2 plus 5 is 11. So far CGHE is the path of lowest weight, or the shortest path. So I can't see any others there. So just try and identify all the different paths. So going this way, there's no chance going backwards. You end up with the weight of the path being greater than 12. So CGHE would be the answer there. So CGHE, and that's equal to 11. Question 40. A museum is planning an exhibition using 5 rooms. The museum manager draws a network to help plan the exhibition. The vertices A, B, C, D, and E represent the 5 rooms. The numbers on the edges represent the maximum number of people per hour who can pass through the security checkpoints between the rooms. What is the capacity of the cut shown? Okay, so here's the cut. Now, the cut is meant to isolate the source from the sink. Okay, we have a 70 here. So that's 70 plus this 90 here is included as well. Okay, so these two edges cut off the flow from vertices C and D. So they're gone. It also cuts off the outflow of C as well. So this 40 does not get included. Since we've cut off everything coming into C anyway, this 40 is not counted. But we have to count the 130, because if we don't cut the 130 off, there's a flow from entry to exit via A, B, E. So we have to add the 130 as well. So adding those together, 70 plus 90 plus 130, we get 290. Okay. Part B. The museum manager is planning for a maximum of 240 visitors to pass through the exhibition each hour. By using the minimum cut maximum flow theorem, the manager determines that the plan does not provide sufficient flow capacity. Draw the minimum cut onto the network below and recommend a change that the manager could make to one or more security checkpoints to increase the flow capacity to 240 visitors per hour. First of all, let's just draw the obvious cuts. Okay. So there's one there. Okay, so that's going to be 80 plus 90 plus 70, which happens to be 240, which is quite interesting. Okay, so which actually equals the inflow to A. We also have this cut here. Okay, and if we add up those edges leading into vertex E, 130 plus 65 plus 45 is also equal to 240. So interestingly enough, vertex A and vertex E are balanced. Okay, so in other words, inflow and outflow are equal, which means that they're maximized. Okay, so let's have a look at a potential cut that we could make. Now we have this cut here. This cut's 290, so that's clearly too big. So let's consider another cut that we could make. I was thinking maybe we can go through here. So maybe this way there. Okay. And we're hoping we can get a number that's in fact less than 240. Maybe. Let's see. So you may have to make this. There's quite a few ways that we can make these cuts. So that's partly the tricky aspect of this type of question, because it's possible to miss a cut. 80 plus 90. Okay, so those two cuts are included. Okay. We also have to cut off the 25 as well. And we also have to cut off the 45. Okay, and we get 240 there. So that's another cut that's equal to the other cuts. So can we come up with another cut that potentially may work? So in other words, a cut that actually gives you a number less than 240. Let's think about maybe one that goes through this way. That way there. Okay, so we have 80. Okay. Plus, now we don't, do we add the 40 there? We do add the 40 there because that's also another inflow into vertex B. Okay. We've got to cut off the 65 because that's an outflow of C, okay, which is an inflow to E. And also 45. And we get 230. Okay. So these four cuts are in fact necessary. Okay, so cutting off the inflow to B cuts off BE. Okay, so these two are important there. And also cutting off these two also cuts off the flow to E via these two edges here. So it looks like 230 may be correct. Now it's only a 2-mark question, so we don't want to waste too much extra time. Okay. Now the recommended change would be to have a look at vertices B, C, and D. Now we know that the inflow to A and the outflow to A is in fact equal. So A is maximized, E is also maximized. Let's have a look at D. The inflow to D is 70, okay, and the outflow of D is also 70. Okay, so vertices A, D, wasn't B actually, it was A, D, and E are maximized. Okay, so if you have a look at vertex C, we got 90 plus 25, okay, is going into C, okay, which is 115, but we've got 105 coming out of C. Okay, I would increase, in fact, this edge here to a capacity of 50. So by changing that to 50, okay, you actually maximize the network. Okay, so we end up with 115 in, 115 out of vertex C. And if you have a look at vertex B, 80 plus 50 going into B gives you 130 coming out of B. So you maximize these two vertices, and that would be the change that would be made. Question 9. Team A and Team B have entered a chess competition. Team A and Team B have 3 members each. Each member of Team A must play each member of Team B once. Which of the following network diagrams could represent the chess games to be played? Okay, so this one, probably best to sort of visualize what's going on here. So if we had, let's say one of the players, let's say Team A, player 1. So this represents one of the vertices. Okay, so one of these dots. That player has to play one game with each of the players from Team B. So let's call that Team B player 1, Team B player 2, and Team B player 3. Now, let's go back to vertex A1. So this is Team A player 1. Think about the degree of this vertex. The degree is the number of edges that basically enter or sort of leave a vertex, or the number of edges connecting to a vertex. And the degree here is equal to 3. Now, go back to each of these options. let's have a look at option A. The degree of each of these vertices is 2, so it can't be A. Option B, each of these vertices has degree 3, so it's in fact option B is in fact the answer. But let's have a look at option C and D quickly. The degree of each of the vertices in option C is 4, so it can't be C. And option D, well, you got a player here playing 1, 2, 3, 4, 5 games. That's not going to work. Okay, so it's option B. Now, if I wanted to label each of the vertices with the team and player number, that could be A1. Okay, and A1 is playing B1, playing B2, and also playing B3. Okay, A1 does not have to play obviously A2 or A3 because they're on the same team. Likewise, A2, okay, can play B3, player A2 can play B2, and player A2 can play B1. And this leaves us A3 here, where, so player A3, so team A, player 3, can play team B, player 1, team B, player 2, and team B, player 3. Question 18. The diagram represents a network with weighted edges. Part A, draw a minimum spanning tree for this network in the space below and determine its length. So to answer this question, I'm going to use Kruskall's algorithm. I find Kruskall's algorithm to be simpler than Prim's algorithm in terms of implementation. We just choose the edges in ascending order, ensuring that as we choose these edges, I'm going to highlight them actually, that we're not introducing any closed paths or cycles. So let's have a look at the edges just by inspection. The lowest weight edge is GH. So I might just highlight that. And the next highest edges in weight are weight 2s. So we have the FGs, FH, we've got FD, we have FC, we've got ED and AB. So that's sort of the next highest weight, okay, up from 1. So I might highlight FG, okay, FD, FC. Now we can't highlight FH because that would introduce a cycle, cycle FGH. Okay, so we've just got to be careful with that one. So we can't highlight that. We can highlight ED, certainly can do that. And it's still a tree, okay, it's not yet spanning. We've got AB as well, okay. So that's all the edges of weight 2 that we can highlight without introducing a closed path. Now let's have a look at the next highest weight edges. So up from 2, we have edges of weight 3s. So we can't choose CD because that'll introduce a cycle, okay. We can either choose BE or we can choose BC. There's multiple answers to this, okay. So there's probably, there's several, there's probably more than 2, but the minimum weight will be the same though, okay. So I'm just going to choose BE, and that is now a spanning tree. So spanning means all the vertices are now connected, and it's a tree because there's only one way to go from any one vertex to any other vertex that we choose, okay. So drawing the minimum spanning tree, okay, so all the highlighted edges I'm going to draw here. So it doesn't have to be to scale, but I'll just try and draw it as neatly as possible. Okay, so E, we have a D here, F somewhere here, okay, and C's up here somewhere. Again, doesn't really matter, as long as you try and keep it neat and tidy, of course. Okay, and we got H there. All right, now something else, just to sort of make sure that, well, one way to kind of make sure that you've done the right thing is if you count the number of vertices, let's count them, 1, 2, 3, 4, 5, 6, 7, 8 vertices, there should be 7 edges. 1, 2, 3, 4, 5, 6, 7, okay? So that's one of the rules of a minimum spanning tree, or one of the, I guess, conditions or one of the characteristics is that if you count the number of vertices, if it's a minimum spanning tree, there'll be 1 less edge. So if there's 10 vertices, there'd be 9 edges. If there's 4 vertices, there'd be 3 edges. That would be the number of edges needed to connect it up in a tree. All right, let's draw it in now. So AB, that's 2. And I'm going to keep a running tally here, so or just sort of write down the weights of these edges, so, and then add them up at the end. Okay, we got BE. Okay, that's 3. Okay, plus 3. So I'm just writing it there. You can't see that on the screen there at the moment. Okay, we have ED. Okay, that's 2. All right, and we got FD. Okay, that's another 2. We have CF. Okay, that's another 2. All right. And we've got FG. Yep. And that's another 2. Okay. And finally, GH. Okay. And that's a 1. Okay, so hopefully that looks correct. I haven't missed anything. Count the number of edges again. 1, 2, 3, 4, 5, 6, 7. Yep, 8 vertices, 7 edges, so I've got them all there. Now let's add them up. So 1 plus 2, 3, 3 plus 2 is 5, 5 plus 2 is 7, 9, 12, 14. Okay, so that's equal to, so I've just ran out of space in this box. Okay, length, minimum length of the spanning tree is 14. Now there is a part B. Okay, so part B, 18B, the network is revised by adding another vertex K. Edges AK and CK have weights of 12 and 10 respectively. Okay, so that just means in that order. So AK is 12, CK is 10. And it's seen on the diagram here. So this is the vertex that's been added, vertex K. What is the length of the minimum spanning tree for this revised network? Now, adding an extra vertex means we have to add an extra edge. So I might just put part A back just to show you part A again. Okay, we're adding K up here somewhere. So that's vertex K sort of between A and B, or just just above vertex B, in fact, right, somewhere here. And it's connecting it's connecting to vertex A and vertex C. Now, in order to ensure that it's a tree and not a cycle, we have to pick either the 12 or the 10. Now, in order to ensure that it's still a minimum spanning tree, in other words, all vertices connected, but with the minimum possible weight edges, okay, in a tree configuration, we choose this one there, okay. There's no point picking the 12. We choose the 10. There's one of the two. They're the only two options we have to connect K to the rest of the network. So the length of the minimum spanning tree for this revised network, the existing network from part A was 14, and we add 10 to that, and that gives us now a minimum weight of 24 for this revised network. Question 26. The preparation of a meal requires the completion of all 10 activities A to J. The network diagram shows the activities and their completion times in minutes. Part A, what is the minimum time needed to prepare the meal? So let's go through and do the forward scanning exercise here. So starting from 0, so that's at the start, the 0-minute mark. Activity A takes 14 minutes. Activity B takes 6 minutes, but activity C takes 8 minutes. With forward scanning, we take the higher of the two numbers. So that vertex is reached at the 8-minute mark. So activity D takes 12 minutes plus 8, okay, and that takes us to the 20-minute mark. Activity E takes 6 minutes. From the 20-minute mark, that takes us to the 26-minute mark. We have a 14 here already, but we take the higher of the two numbers, or the 2 times. So I'm going to put 26 here instead. Activity F takes 10 minutes. From the 26-minute mark, that takes us to the 36-minute mark. Activity G takes 9 minutes. From the 20-minute mark, that takes us to the 29-minute mark there. But we can reach this vertex through activity H as well. So 36 plus 8, that gives us 44. Well, we have a 29 there. 44 is clearly the larger number. So we'll put 44 here instead. Now, to get to the finish, we can either go through, in fact, activity J or activity I. In fact, both have to be completed, but comparing the 2 times, 36 plus 7, that takes us to the 43-minute mark. Okay, but we're still not complete yet. until activity I is completed. 44 plus 2 is 46, so that's the higher of the two numbers. So the minimum time needed to prepare the meal is 46 minutes. Now part B lists the activities which make up the critical path for this network. So this is where we do the backward scanning. So backward scanning, just think of it as forward scanning but totally in reverse. Instead of taking the larger of two numbers or multiple numbers, we take the smallest this time. But we're going against the flow of the arrows there, against the direction of the arrows. So starting at the 46-minute mark, going through activity I or back through activity I, 46 minus 2, that gives us 44. Okay. Now 46 minus 7 gives us 39. Okay. However, to get to this vertex here, we can go back through activity H. So 44 minus 8 gives us 36. So we rub out the 39 or cross it out, and we're going to put 36 here instead. Now, going back through activity F, 36 minus 10, that takes us back to the 26-minute mark. Okay. Now, 26 minus 6 gives us 20. However, we can get to this vertex via G, so 44 minus 9 is 35. 35 is higher than 20, so I'm just going to leave the 20 as it is there. Remember, with backward scanning, if there's a multiple path or a multiple way to get to a vertex, you take the lower or the lowest of the times that you've found. 20 minus 12 is 8, so that's fine. So we can leave that there because there's only one way to get to this vertex. And then back to the start, 8 minus 8, that gives us 0. We also have 26 minus the time for activity A, 26 minus 14, that gives us 12, but 0 is clearly less than 12. So again, we take the lower of the two numbers. So the activities which make up the critical path for this network, okay, we've got this one here, C. Okay, in fact, I could highlight this and it might make it just easier to see. So we've got that one there. Basically, you're looking for the earliest start time or the latest start time where they're identical. So the two numbers are, in fact, the same. So activity D through activity E, okay, through activity F, through activity H, and then through activity I. Okay. So it's C, D, E, F, H, and I. Okay. Finally, part C. Okay. So complete the table below, showing the earliest start time and float time for activities A and G. So the earliest start time, I think that's fairly simple to fill out. So why don't we do that first? So the earliest we can start activity A is at the 0 minute mark. So why don't we do that? And just write that down. So 0 minutes. Activity G, the earliest it can start is at the 20-minute mark. Okay. Now, the float time, the way I work it out, and there's multiple ways of doing it, but I take the latest start time minus the activity time of the particular activity we're looking at. So the latest start time of the activity following the activity that we want. So I take this number here, so the bottom number after A, minus the activity time of A, then minus the earliest start time of A. So 26 minus 14 minus 0 is equal to 12 minutes. Okay, so I've just written that there, 26 minus 14 minus 0 is 12. And for activity G, okay, 44 minus 9 minus 20 will give us the float time for G. So 44 minus 9 minus 20, okay, and we'll get 15. Okay, and that's that. Question 30. The network diagram shows a series of water channels and ponds in a garden. The vertices A, B, C, D, E, and F represent the 6 ponds. The edges represent the water channels which connect the ponds. The numbers on the edges indicate the maximum capacity of the channels. So part A, determine the maximum flow of the network. And there's a part B here. A cut is added to the network as shown. Is the cut shown a minimum cut? And give a reason for your answer. So let's go back to part A. So these two questions are definitely connected. Determining the maximum flow of the network. Now notice that it does not state to use the maximum flow minimum cut theorem. In other words, you don't have to use cuts if you're not comfortable doing so, because sometimes it might be difficult, or you may actually miss the minimum cut, because it's possible that there might be 5, 6 or more cuts that are possible in this network. So I'm going to use numerical methods here, and I can do this fairly rapidly. So I try and identify the paths from source to sink. So this is in fact our source here, okay, and this is our sink. Okay, so this is where the water's all flowing in the end. Okay, so notice we've got 350 there. We've got an edge here that's 300. There's an edge here that's 50, feeding this vertex here. So inflow and outflow is equal there. So F is maximized. The inflow to A is 350. The outflow of A is 350 in terms of the capacity at least. So A is already maximized. So let's work out the simplest possible way to get from A to F first. So we can go A, CF. Okay, and ACF, and in the path ACF, the smallest edge, or the lowest weight edge, is 50. So the weight of that, the capacity of that path is 50. So subtract 50 from everything, so that's 150. Okay, and this would be 300 then. Okay. In fact, I probably wouldn't even need to worry about that number there. Okay, anything past F. So another path that we could use that's as simple as possible, we could go A, B, E, F. Okay, so A, B, E, F. So again, we've got 75. That's the lowest weight edge that I can see in that path. Okay, so that becomes 0. And if we subtract 75 from everything, so AB, 150 minus 75, so that's 75 there. And EF, so that's going to be 225. Okay. I'm not even going to bother with this number here. So, in fact, I may actually, it's not actually of any importance in answering this question at this point. All right. Okay. Any other paths that we can see? So, again, try go for the simplest possible path. So we can also do A, C, B, E, F. Okay. Or we can do A, B, D, E, F. In fact, why don't we do that? So A, B, D, E, F. Okay, we've got 75, 50, 125, 225. 50 is the lowest. Okay, so if we subtract 50 from everything, that's going to be 25. Okay, so DE, so if we subtract 50 from that, that'll make it 75. And 225, that'll make it 175. Okay, so again, let's find another possible path from source to sink. So we can go A, C, B. No, we can't use any of these anymore. There is another possible way. We could go A, C, E, F. In fact, we didn't see that before, or I didn't see that before. A, C, E, F. And we've got 150, 100, and 175. So that's 100. Okay. So if we subtract 100 from everything, okay, and that'll make it 50 there, and EF, so that'll make it 75, okay. And I think that's it. There's no other way to get from A to F. So we've covered all the parts. If we add all those numbers up, okay, so all those capacities 50 plus 75 plus 50 plus 100, and we get 275. Okay, so the maximum flow of the network is 275. Okay. Right, now that takes us to part B. So a cut is added to the network as shown. Is the cut shown a minimum cut, and give a reason for your answer? Well, let's work out the capacity of the cut. Okay, so remember, we've also got to cut the edges that are running sort of in the same direction, and that's sort of dependent on which vertex we're talking about. So you can see that the cut cuts the 200 or AC, and it cuts BC as well. So cutting AC, that cuts the inflow to C. Okay, so that's an inflow. If it's cutting the inflow, then you don't need to cut the outflow. So the 50 does not need to be counted. So we're actually counting the 200. We're dismissing or omitting the 50, okay? But we're cutting the inflow to D, and by cutting the inflow to D, you're also cutting the inflow to E, but we also have to cut the 75 as well. So these two numbers here, or these two weights here, are important. So 200 plus 75 plus 50, and if you add all that up, so 200 plus 75 plus 50, and we get 325. Okay, now if the cut is a minimum cut, it should be equal to the maximum flow. So the cut is not equal to the maximum flow. Of 275, therefore not a minimum cut. Question 2. Consider the network diagram. What is the sum of the degrees of all the vertices in this network? The rule here is the sum of the degrees of all the vertices is equal to twice the number of edges. Let's count the number of edges. 1, 2, 3, 4, 5, 6, 7, 8. 2 times 8 is equal to 16, so the sum of the degrees of all the vertices is equal to 16. Therefore, the answer is option D. Question 23. The network diagram shows the travel times in minutes along roads connecting a number of different towns. Part A. Draw a minimum spanning tree for this network and determine its length. There are 8 edges that need to be connected, which means 7 edges need to be chosen, either using Kruskal's algorithm or Prim's algorithm. I've chosen Kruskal's algorithm for this solution. The highlighted edges are the edges that I've chosen, from the lowest weight to the highest weight, and the numbers here that are circled refer to the order in which the edges were chosen. So I've chosen this edge here between Minor Town and Wall Town, so that's number 1. This edge I've chosen as number 2. Number 3 is here. Number 4 is here. Number 5 is here. Number 6 is here. And number 7 is here. Now, drawing the minimum spanning tree might look something like that. And the length of the minimum spanning tree is just the sum of the edges that were chosen. And that equals 160 minutes. Part B. How long does it take to travel from Queenstown to Underwood using the fastest route? Part B was answered by inspection, and it does not necessarily have anything to do with Part A. It's important to note that the minimum spanning tree does not necessarily give the minimum path or the shortest path between any 2 vertices. Referring to the original network diagram, we can see that there's many ways to go from Queenstown to Underwood. And you need to select the path that is shortest, or the one that takes the least amount of time. So we can either go via Kingsville, so Queenstown, Kingsville, Underwood, that's 30 plus 65 is 95 minutes. And there are other ways as well to go from Queenstown to Underwood. So by inspection, Queenstown to Minortown to Underwood is 65 minutes, so 45 plus 20. And that gives the fastest route. So Queenstown, Minortown, Underwood, 45 plus 20 is equal to 65 minutes. Question 36. A project requires completion of 11 tasks, A, B, C, through to K. A network diagram for the project giving the completion time for each task in minutes is shown. Part A. Find the minimum time to complete the project. The minimum time to complete the project is found by completing the earliest start time, or EST, for each task. So starting here, after task A, we're at the 5-minute mark. After task B, we're at the 8-minute mark. 5 plus 7 is 12. 12 plus 2 is 14. Now 14 plus 3 is 17, but 8 plus 6 is 14. We write the higher of the two numbers when determining the earliest start time. Now from this point, 17 plus 5 is 22. 17 plus 6 is 23. Again, there are two ways to get to this vertex, either 22 plus 8, which is 30, or 23 plus 3, which is 26. We write the higher of the two numbers, which is 30. 30 plus 10 is equal to 40, and we're at the finish. So the minimum completion time is 40 minutes. Part B. State the critical path for this project. The critical path for this project may be found by completing the latest start time, or LST, for each task. Starting from the finish and working backwards, from the 40-minute mark, subtracting 10, we get 30. 30 minus 8 is 22. 30 minus 3 is 27. Now when there are two ways to get to a vertex, we write the lower of the two numbers. So it's the opposite of finding the EST for each task. 22 minus 5 is 17. 27 minus 6 is 21, and the lower of the two numbers is 17. 17 minus 6 is 11. 17 minus 3 is 14. 14 minus 2 is 12. 12 minus 7 is 5. And 5 minus 5 is 0. And the critical path is found by locating the vertices where the numbers, top and bottom, are identical. And I've highlighted them here. So the critical path is A, C, D, E, G, J, and K. Part C. A new task X is to be added to the project. The earliest starting time for X is 17 minutes, the latest starting time for X is 18 minutes, and X has a completion time of 12 minutes. Add task X to the given network diagram above and state the float time for this task. Task X is not on the critical path because its earliest starting time is different to its latest starting time. The earliest starting time for task X is 17 minutes, and that gives us a clue as to where to locate task X on the network diagram. Also note that task X has a completion time of 12 minutes. Here is task X on the network diagram located between this vertex and this vertex. The float time for task X can be found by taking the LST of task K, subtracting from that value the completion time of task X and the EST, or the earliest start time for task X. So 30 minus 12 minus 17 is equal to 1. Therefore, the float time for task X is 1 minute.